to
City of Wilkshire. Yes, it's so
no.
maybe
Today I want to talk a little bit about high pressure pneumatic systems used aboard aircraft. It's kind of difficult to define demarcation points for what's considered to be low, medium, and high pressure. So you'll kind of have to bear with me. But what we use aboard aircraft for high pressure air might be used for emergency purposes, and we might use it in order to maybe as an alternate source of available pressure for most of the hydraulic components that might be used in an aircraft. The sources can kind of vary as well. If we're talking about a standalone compressor, we're talking about something that's capable of supporting maybe 3,000 psi of air pressure. And if we're talking about maybe using bleed air in order to provide for high pressure air, usually the regulated bleed air pressure can vary maybe from, I don't know, 250 or 300 psi on down. But so the sources can kind of vary. What I want to talk about is pretty much a standalone source of air pressure, just to kind of limit the discussion to that, and kind of compare it with hydraulic systems overall. Some of the big advantages that we have with high pressure pneumatics would be over hydraulics, would be reduced fire hazard. If you're talking about hydraulic fluid that is flammable, like LH5606, air, although it contains 21% oxygen, is still less of a hazard in handling, or at least dealing with, than flammable liquid. So there's one big advantage anyway with reduced fire hazard. Also too, if the aircraft supports or has a compressor aboard it that is, provides for self-replenishment of the air, so they're taking ambient air and then pressurizing it, one big advantage would be a limitless supply of fluid. If you look at a lot of Russian aircraft in particular, those aircraft sometimes sport compressors that are integral with the aircraft, so they replenish a flask that they have aboard the airplane. An example would be something like a Yak-50 or a Yak-52. They have a integral storage tank, and they have a compressor that's driven by the aircraft engine. So you're replenishing the flask. The big advantage of that, obviously, is that you don't really run out of air. As long as the compressor continues to function and is able to fill the cylinder or flask, you don't really have to worry about air. So one concern for aircraft that operate out of conditions where they don't have regular servicing facilities for replenishment of hydraulic fluid. And it kind of explains why the Russians or the Soviets kind of do that thing. Also, less weight. Since you're not, if you're comparing it with a hydraulic fluid system, you're not carrying around the weight of hydraulic fluid that would be held in the reservoir and the bulk of the hydraulic circuit. So you're saving a little bit of weight there. There's also one big difference in many of the high pressure systems. There's no recovery of that air. Once it's used to provide for its function and maybe making an actuator work, the air isn't recovered like we typically have in a hydraulic circuit that circulates back to the reservoir. The air is vented via usually a selector valve overboard, and then that's the end of the hunt. There's no real reason to recover it. Also too, you know that we depend on pressure in a hydraulic system primarily by confinement of a liquid. If we develop a small pinhole leak in a statically pressurized container, that container loses pressure pretty quickly. But there's a little bit of a difference with air that's under pressure. When you have a small pinhole leak, it may take a tremendous amount of time for you to deplete the pressure that's in the container. So it behaves a little bit differently than statically charged containers that are full of liquid. Also, maybe another reason too for maybe aircraft that have systems aboard it that operate in cold climates, you don't have the sluggish nature of congealed hydraulic fluid. So you know, as most fluids get cold, they change their viscosity pretty rapidly. And in the case of oils like hydraulic fluid, there's some change in viscosity, so it's going to become more sluggish in operation. So it leads to some problems. Again, you don't really have that with pneumatic systems. There is a big disadvantage in using pneumatic air pressure over high pressure hydraulics. And one thing would be the accumulation of moisture. When you're pressurizing air to the great degree that you are, maybe with a 3,000 psi compressor, it's a lot like squeezing a sponge that contains water. What you're doing is you're allowing the moisture to eventually condense as a result of compression of that air. And regardless of what temperature you're at, there's always some available moisture that's in the air. But when you compress the volume of this room into something the size of a bucket, the available moisture is going to condense and it's going to be a problem. Why is it a problem? When the aircraft goes to altitude, the water freezes, and that can cause blockage in lines. Secondarily, the other problem is that the moisture could be considered as a possible source of corrosion. But most importantly, probably blockage of components when it freezes at altitude. There's another problem too. If you look at most of the high pressure pneumatic systems, assuming that they're not used for emergency purposes, they're used for continual use of pressure to make something function, the system lubrication kind of becomes an issue. A lot of the actuators are fitted with Teflon type seals in order to be able to slide without the addition of hydraulic fluid. With a hydraulic system, the natural lubricating qualities of the fluid are sufficient to prevent friction from becoming a problem. But with a lot of high pressure systems where pneumatics is used exclusively, their seals and the actuators have to be designed so they don't provide for lubrication directly. Okay, so that's what I can tell you. If we're using a compressor to furnish high pressure air, this is kind of a generic picture showing you a two-stage air compressor. And in many cases, we draw air from an ambient source. So we take ambient air into the first cylinder. As the crankshaft rotates or revolves in the compressor, it causes the piston to be drawn down and air enters into the first chamber, the first cylinder of the compressor. When the crankshaft revolves, when it turns, the air is compressed in that cylinder and is prevented from leaving by the method of use of a check valve. And then we deliver the air into a second stage cylinder. And as the crankshaft continues to revolve, the air that's been brought into that second cylinder is further compressed and ultimately discharged into a storage bottle. This would be a typical scenario for what you'd have like maybe on a Yak 50, where they got a multi-stage compressor. The key thing to remember here is that in order to prevent reverse flow of air, they use check valves in order to do it. Some of the check valves that they have aren't necessarily check valves as you would think of them. Some of them are flapper valves that work as like reed valves in order to control the flow of air. So if you were to take the cylinders apart on the compressor, you'd find out that the cylinders contain reed valves at the ports in order to prevent reverse flow of air. There's a big advantage also in driving a compressor if we were to compare it with multiple of sources. If we were to look at an air compressor that's being driven by an electric motor versus one that's being driven by a hydraulic motor, there's a huge difference, and the big difference is safety. If the compressor should stall for any reason or bind, if you've got an electric motor that's driving the compressor, the armature of that electric motor can cause arcing and sparking in its field. So there's a definite fire hazard. In the case of a high pressure compressor that's being driven by maybe a hydraulic motor, well, you're safe to a degree. In the event that the compressor stalls, you know that hydraulic systems usually have a relief valve in the system circuit. The hydraulic fluid isn't impeded in any way. It goes back to the reservoir through the relief valve. So you don't really have the problem of stalling the compressor and creating a huge fire hazard on that hydraulic motor. So there's a big difference. Also note too, most of the compressors that I've seen have multiple cylinders in it for compression. And we've got two that are out in the shop. One of them is a 4-stage compressor. The other one is a 3-stage. It's easier to compress air in baby steps than it is to take just air and compress it with just one or two pistons in compression. So if we can progressively reduce the volume in order to increase pressure, it's probably easier to do it that way than just by having just one stage. So that's what I can tell you. Let's take a look at the compressor, one of the compressors that we have out in the shop. This one was made by Walter Kitty, and that particular one is in fact driven by a hydraulic motor. And it's a 4-stage compressor. And the hydraulic motor is mounted on the back of it. It's a bent axis motor that operates the opposite way that a pump would. So we poured hydraulic fluid into the motor. The motor then causes a rotational force on the crankshaft and the compressor begins to operate. That Walter Kitty compressor can also be fitted with an electric motor. If you look in the spec sheet for that compressor, you can see they have an option for it. That particular compressor that we have came from a military aircraft, and if you look to see maybe the potential uses for it, it's kind of interesting to see what it was used for. In the F-4 aircraft and other military aircraft, they had to provide for canopy sealing. And strangely, they didn't use reduced bleed air pressure in order to inflate the seal on the canopy. But they did use reduced air pressure to seal. So this was a source of air pressure in order to provide for that. And in addition to that, some of the F-4 aircraft are equipped with a strange nose gear extension system that they use for carrier-borne takeoff. In order to inflate, in order to provide for the aircraft to take off in a short takeoff roll aboard a carrier, they inflated the nose gear of the aircraft, the strut, with a source of air that came from here, and then it provided for an angle of attack that would allow the aircraft to get to flight with a short takeoff roll. Afterwards, the air in that strut was released, and then the aircraft would make a normal landing aboard the carrier, but they had to increase the angle of attack for takeoff. They may have also used this compressor for maybe displacement of ordnance aboard the aircraft. So, but anyway, that's what I've kind of discovered for it. They store the air usually in a flask assembly. The flask or the sphere is protected usually by wire wrapping it in order to prevent it from, if it should be penetrated, from creating a hazard, but it stores high pressure air. But anyway, that's what we have. The other compressor that we have in the shop is a 3-stage compressor. They control the speed of the motor in that particular device by means of a flow control valve. It controls the volume of hydraulic fluid going to the motor. So regardless of whatever the system pressure might be in the hydraulic circuit, the motor is regulated at a constant speed by means of a flow control valve. Some motors might be governed, but neither one of them are really internally governed. Some motors have flyweight governor systems in order to control their speed, and the simple way to do it is just by using a flow control valve at the inlet of the motor on that 3-stage one. The 3-stage compressor has an interesting history too. It came from a B-29 aircraft. I don't know what they used high pressure air for in that aircraft, but it's a relic that came out of the San Diego Aerospace Museum. So anyway, just a little bit about the motor or the compressor. There are several things on that compressor that provide for cooling. If you look at it, it's got a fan. The fan, it should be turning with the crankshaft. Obviously, the reason that we have it in the shop is because the crankshaft's busted. So if you're able to turn the fan, without anything attached to it, that's not correct. There should be load on that fan as the motor turns the compressor. So I'm sure the shaft is broken on the compressor. Drive shaft is broken. But the fan should rotate as when the compressor is operational, when the motor is turning it. And that provides for cooling. In addition to that, that compressor has its own integral lubrication source of oil. If you look at the very bottom underneath of the hydraulic motor, you'll find a tank. And that holds oil that's segregated for use in lubricating and cooling the compressor. There's also a pump that's installed near the drive end of the pump, near where the fan is at, and that provides for pressure lubricating the oil system of that compressor. So it's oil lubricated. The oil returns back to the tank. Anything else that's kind of peculiar about it? There's a valve assembly, and you can't make it out very well here, but it's at the very bottom of the compressor. This would be at the discharge of the fourth stage air. And at that point, that valve that they have mounted there is kind of an unloading valve that they'll be using in the circuit. It's dependent upon being closed by means of oil pressure that's in the compressor. So it's an oil-activated valve that we have and if there's no oil present, the diaphragm that's inside of that valve won't be pushed over. And what it does is it provides for the fourth stage air to be delivered overboard rather than to the storage tank. So it's a dump valve if you want to think of it that way. But it's an intentional safety device. If there's no lubricating oil being developed or pressure developed in the lubricating oil circuit, it provides for a means of exchange, getting rid of the fourth stage air directly overboard rather than trying to force it into a container for pressurization. So that's what they have. Anything else for cooling? Obviously the cylinders are finned, and it's finned for cooling. If you look at the interconnecting lines between the stages, you can see that they've also got the interconnecting lines coiled. That adds additional surface area. And it's by no accident that the device is painted black. You'll notice that with a lot of things, they sometimes control heat by means of temperature, by color. In this case, they're attempting to radiate heat out of the compressor, so they've painted it black externally. And so just like a frying pan works with food, what they're trying to do is trying to liberate the heat to the ambient air by painting it black. So a lot of things that are kind of going on for cooling. This is the storage tank that they use with this type of compressor, if they have one. In this case, it's a sphere. In many cases, it's wrapped with wire, and there's usually a tube that goes down near the very bottom of the container. The idea is we have to provide for initial, or I should say secondary moisture separation by means of a siphon action. So in the bottom of the container, you can see extending up from the top of the head, they've got a drain tube. The drain tube works by siphon action. As the moisture is accumulated inside of the sphere as it comes off of the fourth stage, the moisture sits down at the bottom. The drain valve itself is located up at the top of the container. When you open the drain fitting, you're using the prevailing air pressure that's inside of it to force the water or collected moisture up the tube and then out the drain. So it works pretty much by siphon action. That's how it functions. There's a lot of different sizes of these flasks. There's one particular size. It's a 400 cubic inch cylinder or sphere. There's another one that's 400. But again, it's primarily for storage of air in it. These flasks are also used in one particular case as well. The early Cessna aircraft, the Cessna 300s, had a non-replenishable air storage tank aboard the aircraft. What they did was they used high pressure air reduced in pressure in order to be able to inflate pneumatic de-icer boots on the wings. But there was no replenishment provided in the aircraft. The reason that they had to use a sphere under high pressure is simply because in order to allow enough duration of time for application of the boots, they had to have a high pressure that they could reduce in order to make the boots function. Periodically, the sphere was replenished on the ground. But okay, so that's what I can tell you about high pressure anyway. Some of the containers that we store pressure in are actually cylinders. They may have an integral charging valve on them, and it allows for a source of high pressure air to replenish the cylinder on the ground, usually from a ground mounted compressor. The control valve is usually their selector or their release for the air that's contained in the cylinder. One thing that's also kind of important too with high pressure pneumatics, the valving that we use is similar, not identical, but similar to what we have used in hydraulic systems. We have selector valves, but again, the big difference is we don't recover air back to the reservoir. So the selector valves are designed to usually port air overboard once they're used, maybe for emergency application of a component. And but we still have check valves. They may look like flappers. We may have restrictors that are used in the circuit. We may have shuttle valves that are used as part of the circuit. But there's a lot of similarity that we have. Relief valves, same deal. If we have high pressure air, we have to ultimately control it. So we'll have high pressure relief valves that are designed to vent that pressure if the pressure becomes excessive. And That's it. Expect to find on a lot of the cylinders to be charged. You might find near that area or on the cylinder itself a placard that provides for charging pressure based on ambient temperature. You can see that they've got some curved lines that are on the chart, and again, what it does for you, it provides for the proper charging pressure. So should you wish to charge the cylinder under something other than normal ambient condition, 70 degrees or so. But anyway, some of the valving. These are slide type selector valves, and they're showing you one position of the selector for application of pressure, and then when the selector is pulled or pushed the other way, usually what happens is the air pressure is vented overboard. So same thing, we're going to have orifice or restricted orifice in order to control flow of pneumatics used in circuits. This is the same picture out of the old 6515 book, just not colorized. Okay, this is what I'll probably ask you to take a look at for the last project in the hydraulic lab. This is a complete high pressure pneumatic circuit that is furnished in the old airframe book, and I've captured a portion of this in the Aviation libraries from an old military manual. And again, this circuit must have been fairly common, not just used for the F-4, but for other military airplanes. It's not used, to my knowledge anyway, for civil aircraft, but it provides a good representative sample of what you might find for high pressure pneumatics. We start out with a controlling device that controls air pressure. Well, if I wanted to kind of pinpoint what that device is, there's a pressure switch that we use in the circuit. It's a switch that's activated, it's mounted on top of a moisture separator inside of the hydraulic, or inside of the pneumatic circuit. But what we'll do is we'll deliver voltage from a circuit breaker and a bus assembly through two normally closed switches. You may wonder what these switches are. The switches are integrated into the door assembly that covers the compressor. They're a part of a safety device or a linkage. If the door is closed, what it allows to have happen is it allows voltage to be made available to the wiper contact. However, when the door is pulled open on top of the compressor, it interrupts the electrical circuit so that no voltage is made available to the wiper on the pressure switch. If you're at home, you kind of realize what happens when you open the maybe the lid of the washing machine or open the door on the dryer at home. Immediately, the action stops. So the idea is, if we have to perform maintenance on the compressor for any reason, we want the door's got to be open, obviously, but we don't want the compressor to be operational at the same time when the door is open. So by having the door closed, the door acts as kind of a shield in the event that the compressor should malfunction. That prevents it from possibly damaging you. So the door closes, and then the wiper or the switch contacts are then closed, and then voltage is then made available to the upper contact, or made available to the contact that's on the pressure switch. Also, you'll notice too that there's a connection point for wiring that goes down to this valve, which is a solenoid dump valve that will ultimately vent the accumulated moisture that collects, that comes off of the air compressor. And we've also got another piece of wiring that comes along here as part of a heater circuit. We have to prevent the accumulated moisture that's in the moisture separator from freezing. There's a blanket that covers the moisture separator. It's just a resistive element. What it does is it just heats the water up above the freezing point of the water, freezing point of water, and prevents the water from freezing. So let's kind of go through the operation of the system. We'll assume that we don't have any air pressure that's being delivered to the flat. So in that particular case, if the door is closed and we have no air pressure, the switch position will be down. And what that does is it provides an electrical voltage to one coil inside of a solenoid selector valve. What that does is it provides for hydraulic pressure to be made available into the hydraulic motor. So the hydraulic motor then begins to turn. As the hydraulic motor turns, it spins the shaft, or the drive shaft of the compressor. Air delivered from the fourth stage then enters into the moisture separator, and whatever moisture is collected at this point will be retained inside of the moisture separator. At this time, when the switch is in the low position, you'll notice that there's no electricity furnished to the solenoid that's attached to the dump valve down at the bottom. So the moisture collects down at the bottom of the moisture separator, and the air passes up a tube and ultimately goes into the flask downstream, all right? So, and also the heating element is provided with power too, so you're heating this chamber, the moisture is prevented from freezing. So, okay, so the fourth stage air comes in, goes into the moisture separator, and then travels on out into the flask. And eventually we reach the limit of pressure. So at some point, the valve is connected to the top of the moisture separator, pushes the switch to the up position. This would be the high switch position, maybe 3,000 PSI or so. At that time, you can see what happens. You now remove electrical power from the solenoid attached to the solenoid selector. What that does is it now prohibits fluid from entering into the hydraulic motor, and also the compressor should stop at that time. Additionally, what you're doing as well in the high switch position, you're now allowing the solenoid to, in this case it's at the 3,000, it's de-energized. So now you're allowing moisture to leave out through the dump valve. The valve up at the top of the moisture separator should be closed at this time, and you're retaining pressure inside of the sphere. So it's kind of an interesting system. Notice also too what they have to regulate the flow of hydraulic fluid. External of the hydraulic motor, they've got a flow regulator. So this is controlling really the speed of the hydraulic motor. So it's not dependent on hydraulic pressure, it's dependent really on flow for operation. They've got a case drain for it too. This would be for recovery of hydraulic fluid for cooling that hydraulic motor. And what else can I tell you about it? Well, the source of airflow. In many of these older high pressure systems, they're not drawing ambient air into the first stage. What they're doing is they're using bleed air that is highly unregulated. And in order to stabilize the source of airflow to the inlet of the compressor, they have to provide what they call an absolute air pressure regulator. So this would be the pneumatic line connection that leads into the first stage. However, it is not ambient air that enters. It's really air that comes from bleed air from the engine. But again, as the bleed air is really unregulated, we have to stabilize the airflow to the source. So they use what they term a absolute air pressure regulator. The FAA will have a test question for you about that. What they want you to remember is that particular regulator is located at the inlet of the compressor. Normally, when you think of a lot of hydraulic regulators, they're integrated into the high pressure circuit, but this particular regulator is located at the inlet of the compressor. Anything else that's kind of unique about the system? Indication of pneumatic pressure is done remotely. You'll notice what they have in the cockpit is just a gauge, okay, but it's electrically wired to another device that they call a transmitter. By doing this or indicating pressure remotely, it's a safety feature. Just like a lot of hydraulic circuits, it's not really wise to plumb directly a board-on tube into the cockpit that sees or is exposed to high pressure fluid. We do the same thing with high pressure air. Rather than use a direct reading gauge that might lead to problems, or at least might lead to a problem with safety, we prefer to have indirect indication. So they use a pressure transmitter down at the bottom. This is an AC circuit, so it's one of two different types of remote indicating systems. It'll either use what they call a Magnuson system for indication or an Autosyn system. Both of those are AC powered. If it was DC powered, it would be using a Selson system. And Selson is kind of peculiar because it uses a permanent magnet that's influenced by a coil. In this case, they use either a magnetic reluctance or they use AC voltage, so three-phase AC in this particular case, but nevertheless, that's it. Also, too, something else, the chemical dryer. This is mounted downstream of the moisture separator. Usually with these systems, you can't just rely on just the moisture separator to hold or contain the moisture. They provide for some secondary means of getting rid of moisture. In this case, they may use like a silica type of compound that's held in a cartridge. When the silica changes color, sometimes that's an indication that moisture is present. When moisture builds up in those silica containers, what color do they change from and to? From blue to pink or red, yeah. You'll notice that they use those same type of silica absorbers sometimes in reciprocating engine applications. When they have to put recip engines into storage, the spark plugs are usually replaced with devices that thread into the spark plug ports that provide for the same kind of function, and it prevents the cylinders from rusting internally. So it usually goes from blue to red or pink when they change color. So that's kind of how they work. Anything else that's kind of unique about this thing? I can't think of too much that I can tell you. They show you, question, go ahead.
Yeah, there's a question. On the, so in the air pressure sending unit, that's a Gordon tube connected to a wiper in that case?
Yeah.
Okay.
Yeah, and you know, people think that board-on tubes can't take high pressure. It's not really true. If it is, it's a board-on tube. But the truth is that they can't take high pressure all at once.
No.
So, yeah, but yeah, they're quite capable of taking high pressure. It's pretty amazing. A lot of them are constructed out of bronze or copper-based alloy. You know, so, but yeah, that's what they do.
Because I'm more used to the DC style, you know, that has a piezoelectric, you know, variable resistance type setup.
Yeah.
Where you input 9 volts or 12 volts or whatever, and it outputs, you know, between 1 and, you know, between 0.5 and whatever volts with DC.
Yeah.
That's what I'm more used to. I understand that.
The Selson system's kind of interesting too. They use a modification of that for the indicating circuit like on the S2F. Rather than, you can kind of see something interesting too. If you remove electrical power from the S2F system that would provide for gear indication, the permanent magnet takes over in the indicators and it drives the indicators toward it would be the, not up and not down would be the in-transit indication. That's one quick way to check for an open circuit when you have those. When you have a break in the electrical wiring, it forces the permanent magnet to seek a position. And in this case, on that gear, it goes to a null, which would be in transit. So, all right. So anyway, you kind of see, oh, there's a wafer charging on the ground too. All right. So that they show the 2 extreme positions of the moisture separator control and the switch. In the low switch position, let's see what they've got. This would be building up pressure into the pneumatic circuit. They're delivering voltage to the solenoid, and what it's doing is it's holding the dump valve closed. So in this position, what's happening, you're building up air pressure and you're allowing moisture to collect or condense down the bottom of the moisture separator. And what's providing for that is when that switch is in the low position, you're delivering voltage to the solenoid selector valve and you're pouring hydraulic fluid into the motor to make that turn. And then ultimately, when we get to the high switch position, what we do is we remove the electric power from the solenoid and the dump valve is now open, and then the accumulated air pressure that's in the moisture separator can't leave. The valve is closed here, but then the moisture can be pushed out, just gotten rid of. And the way that we caused that to occur was when that switch was in the high switch position, it removed the voltage from the solenoid. So in this case, it stopped the hydraulic motor from rotating. Anything else? Oh, at the very top of the moisture separator, the valve that they have mounted at the top has the ability to relieve excessive air pressure. They're showing you this down at the bottom. So if the air pressure in the cylinder or the flask should expand, there's a way for that excess air pressure to get out. So that's it. Oh, regulated temperature for that for the heat blanket is right around 60 degrees Fahrenheit. So again, the moisture really can't freeze at that point. And let's see, what else do we got? Oh, here's an interesting picture as well. This comes out of the Marrow Fluid Power Book. This would be a normally powered hydraulic system. However, they use air under pressure that's retained in flasks in order to provide for an alternate source of pressure. You'd have to replenish the flasks on the ground with a ground support circuit, but they do have a priority valve in the circuit, so the pneumatic lines or the manifold is generally open to all of the components in the pressure manifold. if the pressure should drop off, this valve will be closed for whatever reason, it'll close. And then you have airflow that's trapped in specific parts of the circuit for just emergency use only for some components. What separates the normal and emergency function from hydraulics and pneumatics would be shuttle valves. Every place where they've got these valves indicated, those are shuttles. So normal application of hydraulic pressure is going to be via hydraulics, and the alternate is going to be pneumatics. Kind of an interesting thing. They also have got what they call a combustion starter aboard this aircraft. Combustion starters are kind of unique. They don't really use them too much more in aircraft today, but they did use them in some recip engines, and they did use them in some turbine engine aircraft. Combustion starters rely on the combustion of a propellant charge, and if you look and see how a lot of the military ones work, it looks like a shotgun shell without the shot. What they do is they put in the breech assembly, they put a starting cartridge in the breech and then close the breech, and then they fire it, and then it's enough, generates enough gas and volume in order to rotate the crank of the engine. They do the same thing in some really old turbine engine designs too. But we can also use air pressure that's contained inside of the flask for starting. They don't like to use the combustion starters too much anymore because there's a little bit of a fire hazard associated with them, but you don't see them too frequently used. My old school, the AMP school, had one aircraft that had an engine that was started with a combustion starter, and we had some cartridges. The instructor kept them in his office, for fear that somebody was going to use the thing for what they shouldn't. But anyway, that's what they did.
So when that thing lights off, or when that cartridge
Fires.
fires, what is it? Is it releasing?
It releases the gas, just like in a shotgun shell. The gas, the propellant evolves into a gas. So the gas pressure then is directed into the cylinder through a distributor in order to rotate the crank.
And how many revolutions? Say the engine
Not-
didn't light off.
Not too much.
Would you continuously keep shooting these things? Or?
Well, it could,
We're gonna hand load them, right?
yeah,
Ever seen Flight of the Phoenix?
that's where I'm going.
Yeah, I did. I just didn't understand how that worked.
It's fantasy, but I think you'll get the idea.
Main plot point.
I don't know if I want the whole movie. Let's see if I can get to the.
Got some.
I don't want that either.
Where? Clear. That's number one. Oh. What's wrong?
There ain't nothing wrong with that engine. Maybe you ain't giving it enough juice.
Yeah.
Three.
He should know, shouldn't he?
He does know.
Wait. Wait.
The model builder.
You're wasting the cartridges. We have only 3 left.
I know that. What are you doing? I'm gonna use one cartridge, ignition off, clean out the cylinders. Now! What are you doing? Stop! I forbid you! I forbid you! Stay away! I forbid you!
It starts.
Easy.
So all you talking about this. How about if we do this?
What's the largest radio you can hand prop?
Boy, I don't know, there's many.
I mean, they do, don't they let you do one if it's?
No. I know a guy that was on Midway Island, and I know what they did in order to get engines to start. They put a boot on a rope, and they grabbed the end of the propeller that way in order to get it to rotate.
That's true. That's cool.
Don't ask me what happens when you run out of them. I don't know.
You can reload them?
Reload.
I guess you could.
It looks like a combustion. It looks like a shotgun
It does,
breech.
and that's what it is. So there's no shock, that's all.
And that's the main starting system?
Yeah, started with combustion started. Try this. One time I found something that's kind of cool. No, can't seem to find it. I want to waste a lot of time. That looks interesting, but I don't have time. find it later. Okay, let's talk about, maybe a little bit about something more common. Now, we use pneumatic air in most commercial aircraft for a lot of other purposes. We'll take bleed air normally, and it can come from a lot of different stages. If we're talking about modern aircraft with axial flow compressors, we might pick off air maybe from the 8th stage or the 13th stage, depending upon the flight regime of the aircraft or whatever the speed the aircraft engine is on. Obviously, at the lower stages of compression, you're providing for low pressure air, and at the higher stages, you'll get higher pressure air. The end use of that air is going to be for a lot of different things. We use it in some cases for cross bleed starting. Once we start an aircraft engine, we can use the air pressure that the compressor, the turbine engine compressor has to cross bleed start the other engine. We can also use it for from the source of air from the auxiliary power unit aboard the aircraft, or maybe from a ground pneumatic cart, so we can get air from a lot of different places. What we use it for on the aircraft, we can use it in its regulated condition for anti-icing purposes. We can duct the airflow internally inside of the wing of the aircraft through tubing or ducting and provide a heated source of air for prevention of ice. We can use it for pressurizing a hydraulic reservoir through a regulator that would pressurize the air in it. You could use it for supplying air pressure in the potable water tanks aboard the aircraft. When you have to turn on the tap, it isn't magic that makes the water come out of the faucet. You have to have a source of air pressure that's furnished on the water in the potable water tank to get the water to come out. Anything else that it might be used for? Anything that you could generally make hydraulics used for. But anyway, this is what we'd have for a large commercial aircraft generically anyway. So for the distribution of air. And of course, you're going to have to regulate it in most cases. So expect to find that whatever the use is going to be, it just can't be raw bleed air that's taken off of one stage. It's going to have to be regulated and cooled. Many of the sources of air provide for heat exchangers that are air-to-air heat exchangers. And I'll talk about this in a little bit. Why don't I show you a quick video? This one covers 767 overview and component location for pneumatics. So let's take a look at this.
Found a video of cartridge starting in the English Electric Canavera.
I've got one. That's what I was looking for on YouTube.
I found it.
Okay. It should have a big plume of smoke coming out of the top.
This program is designed to introduce you to fault isolation on the 767 pneumatic system.
Oop.
Fault isolation is provided by
I don't want you to see fault isolation first. I want you to see the components.
This program is designed to introduce you to the 767 pneumatic system by describing the system operation and the function and location of each of the major components in the system. The purpose of the pneumatic system is to supply compressed air for the following user systems: environmental control systems, thermal anti-ice, engine cross-starting, the air-driven hydraulic pump, and the pressurization of the potable water and hydraulic reservoirs. 3 separate sources of pneumatic air provide pressure for the system: the engines, the APU, and the ground cart. The operation of the pneumatic system is controlled from the flight deck. The controls are located on the right side of the P5 panel. The controls on the pneumatics panel are a dual needle indicator, which provides pressure indication for the left and right ducts, the left, right, and center isolation valve switches, the left and right engine bleed air switches, and the APU bleed air switch. Annunciator lights provide indication of system malfunction. The left and right high stage lights, the left and right bleed lights, the valve lights, and the off lights. Circuit breakers for the pneumatic system are located on the P11 panel. Located on the P2 panel, the Engine Indication and Crew Alerting System, or ICAS. The upper ICAS display indicates Level B cautions and Level C advisories for the pneumatic system. The lower ICAS display provides pressure indication on the ECS MSG maintenance page. The primary source of compressed air for the pneumatic system comes from the left and right engines. Both operate in a similar manner. Air is provided by each engine from either of 2 bleed sources: an intermediate pressure stage or a high pressure stage. They are both independently controlled. During climb, cruise, and certain holding conditions, as well as with high gross weights, the intermediate stage is supplying the air. Intermediate stage bleed air passes through a check valve before entering the system. During low power settings, descent, and certain holding conditions, the high pressure stage supplies the air. High pressure bleed air enters the system through a high pressure shutoff valve. The operation of this valve is controlled by the high pressure controller. The controller signals the valve to open or close as dictated by engine high stage pressure. The valve is either full open or closed. It does not modulate. This provides automatic switchover between the intermediate and high pressure bleed sources. When the system is operating using high stage air, the intermediate pressure check valve prevents reverse flow. For most operations, the intermediate stage will be supplying the air. Engine bleed air passes through a pre-cooler. The pre-cooler is a cross-flow heat exchanger which uses engine fan air to cool the bleed air. The 2 airflows are kept separated and are at right angles to each other inside the pre-cooler. The amount of cooling air passing through the pre-cooler is regulated by the fan air modulating valve. The operation of this valve is controlled by the fan air temperature sensor located downstream of the pre-cooler. It senses the temperature of the bleed air and pneumatically modulates the fan air valve to maintain the bleed air at approximately 380 degrees Fahrenheit. The pressure regulating and shutoff valve serves as the interface between the engine bleed air system and the airplane user systems. This valve provides 3 functions in the pneumatic system. First, it regulates the output pressure from the engine bleed system to a nominal 40 psi. Second, it prevents reverse airflow into the bleed air system. Third, it provides airflow throttling for overtemperature control. This is accomplished by venting servo pressure and allowing the valve to move toward close. Overtemperature limiting begins at 450 degrees Fahrenheit by modulating the valve toward close. When the temperature reaches 495 degrees Fahrenheit, the valve will be fully closed. Each of these functions can modulate the valve towards the closed position. Thus, the function with the greatest close requirement will control the valve position. Pneumatic components associated with the engine are located within the engine area, the strut, and the leading edge of the wing. Access to the engine area is provided by opening the engine cowling. The cowling has been removed from the left engine to allow visibility. There are two 8-stage ports on the upper half of the engine. Only the left port is visible from this side. Moving up the duct towards the pre-cooler, the 8-stage check valve. After the 8-stage duct, the 15th stage high-pressure bleed ports. The high-pressure shutoff valve, it is controlled by the high-pressure controller. Moving up the duct, the pre-cooler. Fan air enters the fan air inlet on the right side of the engine, passes through the pre-cooler, and exits through the fan air outlet on the left side. On the right side of the engine, the other 8-stage duct, the fan air inlet. The amount of air is regulated by the fan air modulating valve. Components that are located in the strut area above the firewall are accessed through access doors. Through the right access door, the fan air temperature sensor. This sensor provides control for the fan air modulating valve. Through the left access door, the over temperature switch. Over temperature is indicated by the illumination of the high stage light on the P5 panel. The pressure regulating and shutoff valve. This valve is controlled by the bleed air switch on the P5 panel. The pneumatic duct runs between the engine strut and the wing body fairing. It passes along the leading edge of the wing. Lowering the slats provides access to the area. The left duct pressure transducers are located at the forward end of the wing body fairing, just below the wing leading edge. Removal of the outer panel provides access to the area. The forward left duct pressure transducer. This provides indication on the pressure gauge on the P5 panel. The aft transducer. This provides pressure indication to ICAS on the ECS MSG page. The right pressure transducers are located on the right side in a similar manner. There are two additional sources of pneumatic air, the APU and ground pneumatic carts. The APU provides a source of compressed air for ground operations. Air enters the distribution system through the APU shutoff valve and check valve. These components are located in the tail cone compartment behind the aft pressure bulkhead. The APU air supply shutoff valve is located in the aft end of this compartment, forward of the APU firewall. Access is through the controls bay access door. The APU air supply shutoff valve. An APU control switch located on the P5 panel controls the operation of the shutoff valve. The APU check valve is located in the forward end of the tail cone compartment, just aft of the pressurized bulkhead. Access is through the service access door. the APU check valve. The ground pneumatic cards provide the other source of compressed air on the ground. Located forward of the left air conditioning bay, the ground connectors. Air enters the system from either or both of these connectors. There are 3 isolation valves within the pneumatic system. Each isolation valve is driven by an electric motor to full open or full close. 2 of these valves isolate the left and right engine air distribution systems from each other. Each of these 2 isolation valves has a bypass check valve installed with it. A center isolation valve is virtually identical to the other 2 isolation valves. However, there is no check valve with it. For normal flight operations, the left and right valves are closed and the center valve is open. This center valve has a guarded switch to prevent inadvertent closure and loss of air to the air-driven hydraulic pump. The bypass check valves in the left and right sides of the system allow for flow around the closed isolation valves. This allows pressure from the left and right engines to drive the air-driven hydraulic pump. The left and right valves are located in the air conditioning bays. Access is provided by opening the ECS access doors. Located in the aft end of the left air conditioning bay, the left isolation valve and bypass check valve. It is controlled by an alternate action switch light on the P5 panel. The right isolation valve and bypass check valve are similarly located in the right air conditioning bay. Located in the forward inboard side of the left wheel well, the center isolation valve. This valve is controlled by an alternate action switch light on the P5 panel. There are several control relays that are associated with the operation of the pneumatic system. Some relays for the APU air supply valve are located in the aft cargo compartment. They are located on the P49 panel inside the aft equipment center. Other relays are located in the main equipment center. Access is through the electronics bay access door. These relays are located in the P36 left miscellaneous electrical equipment panel and the P37 right miscellaneous electrical equipment panel. The bleed air control card is located in the P50 electrical equipment file. The air supply bike module is located on the E31 shelf. This is a separate bike module for the pneumatic system. It is a microprocessor-based collector and storage device for faults in the line replaceable units or wiring interfaces associated with the bleed air system. It is capable of storing faults for the previous 8 flights, and in addition, it will verify proper system operation. This concludes the system overview and component location for the 767 pneumatic system. You have been shown the location and function of the major components in the system and have been given a description of the system operation.
Just take a quick look at fault isolation. This uses the bite module.
This electronic malfunction and fault isolation module is built into the airplane and hardwired into the operational circuitry. It is not a pneumatic system controller, but a storage device for faults in the line replaceable units or wiring interfaces associated with the bleed air system. It is capable of storing faults for the previous 8 flights. The bike module is located in the E&E compartment aft of the nose gear. It is mounted on the E3-1 shelf of the E3 rack. It is used for ground testing only. Therefore, the airplane must have electrical power on to operate the module. Pneumatic pressure may be on for the first part of the procedure, but must be removed prior to the verification phase. The face of the module contains 12 indicator lights and 4 switches. 7 of the indicator lights display the major components in the pneumatic system. 1 light indicates malfunctions from previous flights. 2 lights show whether a malfunction exists in the left or right side of the system. A wire fault light will illuminate to indicate circuitry problems. It is related to, but not part of, the major components. A no-fault light will illuminate to indicate that no problems exist at the present time in the system. A test switch provides testing of the module for electrical power and the status of the indicator lamps. A byte step switch processes the module through its memory display procedure. A verify switch checks the actual system hardware interface status. A reset switch clears the electronic memory only after a no-fault display has been illuminated. An instruction decal, located below the display panel, briefly states how the module is operated. The first step in operating a module is to press the test switch. All the lights should illuminate, indicating that power is available, and all the light-emitting diodes, or LEDs, are serviceable. When the byte step switch is pressed, the module will search its memory, beginning with the left side and proceeding through the right, and indicate any recorded malfunction that has occurred during the last flight. For example, these lights indicate a failure in the fan air valve on the left system. Record this data for your maintenance records. Press the switch again. The module will continue interrogation of its memory and stop at each malfunction. These lights indicate a failure in the pressure regulator valve on the left system. Continue to record all data for your maintenance records. Press again. After all the left failures have been displayed, the module will search the right system. These lights indicate a failure in the high pressure controller on the right system. The switch must be pressed after each malfunction is displayed to continue the search and determine the next fault. If any wire faults have been sensed and recorded, they will be displayed along with the corresponding unit. For example, a connector or wire malfunction for the right system high pressure controller is displayed. This is indicated by the additional illumination of the wire fault light. Press the switch again. After the current flight data is completed, any malfunctions recorded during previous flights will be displayed. Notice that the previous flight's light is illuminated. A failure in the high pressure controller for the left system is indicated. Press the byte step switch again. If no lights illuminate, the entire memory has been interrogated and there are no more malfunctions recorded. As an assurance check, press the byte step switch one more time. The first malfunction that was originally displayed will reappear. At this point, the necessary maintenance should be performed on the system. When completed, return to the byte module for checkout. The verify switch is used to check the interface status of the repaired components. Caution: before pressing the verify switch, pneumatic pressure must be removed from the system to avoid possible equipment damage. When the verify switch is pressed, the module checks the interfaces of the system components, not the memory. Notice, a fault still exists after the maintenance has been accomplished. Further work must still be performed. Again, service the affected component on the system and verify on the byte module. When all repairs are completed, the verify switch will cause the module no fault light to illuminate for 10 seconds. After the no fault light extinguishes, the memory of the byte module will be erased when the reset switch is pressed. Then, current flight data and previous flight's data no longer can be recalled. This switch will remain active until either engine is run up to 62 psi HP stage. As a final check to verify that the memory has been erased, press the byte step switch. None of the data lights should illuminate. This indicates that a clean memory is again ready to register and store data on future flights. Remember, pushing the reset switch will not erase the memory until after all necessary maintenance has been performed and verified.
This one?
If you lift up one wing to the starboard engine, it will be exactly the same again. Those spikes sticking up and down the wings, it took me many years to realize that the one of the reasons I couldn't fly.
That was pretty cool, huh?
I would,
All right. If you want to take a look at some aircraft that use air pressure normally for operation of components and also for emergency use, take a look at the Aviation library. I've got some literature that came from a Yak 52 or a Yak 50. This shows one of the schematic circuits for their distribution network for pneumatics. They use a engine-driven compressor in order to furnish the airflow that's stored in a couple of different flasks that they have aboard the aircraft. Even though this is a piston engine aircraft, it's kind of a desirable thing. The brake system operates pneumatically. What else? The engine start system is pneumatic. They use a distributor valve that's mounted on top of the aircraft engine to motor the aircraft engine for starting the engine. And what else? Oh, the landing gear system, both normal and emergency, gear is furnished with air for extension and retraction, or normal extension and retraction and emergency extension. Notice also in the schematic they're using ISO symbols for displaying the valves. Again, a person that isn't really familiar with a lot of the circuitry, at least they can kind of figure out what the valves might be. I've got a crude translation of the Russian version of the description, but the description leaves a lot to be desired. If you want to see that, I've got a copy that's someplace.
Flaps too.
I'm sorry?
The flaps.
Flaps as well?
Yeah, the flaps.
Flaps are. Anything else? No, the flight controls are all mechanical. So yeah, the flaps are also pneumatically operated. Is it pneumatic for down? Is it pneumatic? Does that have a spring for retraction?
It's up and down.
Up and down?
Yeah.
Okay. Anyway, this gives you an idea of the valving that they have in the circuit. And then for a commercial aircraft that you might find used for high pressure pneumatics, there's only one civil aircraft that I'm aware of that uses pneumatic air pressure for direct use for normal function. In this case, it would be a Fairchild or a Fokker F-27. Fokker aircraft were produced in Europe, but then under license, they were produced in the United States by Fairchild. To my knowledge, there's a few aircraft that are still operating, but they're not. I don't think they're still currently produced. I don't know if the follow-on versions of those aircraft also sport pneumatics, but at least this one did. The Army parachute team used to operate out of a Fokker when they went to air shows. In any event, what they use for air pressure, they've got onboard compressors. They've got two onboard air compressors, one driven by each aircraft engine. This is, by the way, a turboprop, twin-engine turboprop aircraft. And what they do is they've got the distribution of air that comes off of the forward stage that goes to a bleed valve. The bleed valve is just like the bleed valve that you have on the compressor that we have in the shop. It senses oil pressure inside of the compressor. If there's no oil pressure available, it'll duct the fourth stage air directly overboard, so in a way unloads the compressor to prevent failure. The airflow ends up going through the distribution network through a moisture separator, then through a chemical dryer, and then through a back pressure valve, and ultimately through a micronic filter, through a check valve, and then it's stored in a storage flask for a primary bottle. And then it's also delivered into two other bottles. One bottle or container is for the emergency source of air, and the other one is for the brakes. Apparently the brakes take quite a bit of volume of air in order to actuate. The end users of the circuit to make things work would be the passenger door. You can open and close the door pneumatically. Normal gear control for extension and retraction of gear. Nose wheel steering is also furnished pneumatically with air. And since it's a turboprop aircraft, they have propeller brakes. The propeller brake is used as a safety feature. Once the engines are turned off, we don't want a windmilling propeller to create a hazard, so we can slow the rotation of the prop or the propeller with a pneumatically operated propeller brake. You can isolate the circuit as well. On the ground, they do have an isolation valve. It's usually safety wired in the on position. The idea is that if you have to perform maintenance on the components that are downstream, it allows you to turn off the flow of air that will be delivered from the cylinder so that you can do what you need to do on the end use of the components. This is pretty much the only aircraft that I know of anyway that is powered directly with air under pressure for its normal systems, but anyway, kind of unusual to see it. More often than not, when we're talking about pneumatics, we're talking about emergency use of air. There is one, for Boeing aircraft, this is also pneumatically actuated. They have an assisting mechanism to leverage the door open, the passenger door, as an emergency opening procedure. And they've got a flask that contains gas under pressure in order to operate the door. The flask, I think, might be pressurized with nitrogen. I'm not quite sure, but it may be nitrogen in order to make it work. But it's a leveraging mechanism that will, in fact, help to assist in opening the door. As the latch assembly and the door is open from the inside, what happens is there's a striker, or at least a spring-loaded cartridge, that pierces a foil strip that's on top of the cylinder, and that releases the gas pressure directly to a pneumatic actuator that turns a gear, a sprocket, in order to leverage the door open. It can only be used from inside the aircraft. It can't be actuated from outside, but it's a device that will assist in opening the door. So it's emergency only. No replenishment aboard the aircraft directly. It has to, the bottle or the sphere has to be replenished on the ground. There's a gauge that indicates pressure for it, so you can see at least what pressure is retained inside of the cylinder. Something else that they use, oh, here's a close-up view. As you open the, or begin to initially push the door open, that spring-loaded cartridge eventually is cocked, and then eventually it's released in order to foil, pierce the diaphragm, or the piece of foil that they have on top of the cylinder. Anything else that's pneumatic? Some Boeing aircraft, or most of them, have an escape slide. And the escape slide receives usually a gas charge in order to inflate the inflatable device. More often than not, it's going to be a nitrogen charge that's retained. And we can use this also for some aircraft that require pop-out floats, but they've got a gas charge in them. You may wonder also, too, you know, you take a look at the size of the container that is designed to inflate that inflatable. There's no way in hell that you have enough gas pressure, even in that small cylinder, to make that slide deploy, or at least fully inflate. There's a trick, and the trick that they employ is what they call an inflation valve with an aspirator. The aspirator is an assistive device that works like a venturi. They use the gas charge inside of the cylinder to flow through the throat of that aspirator to pull ambient air into the inflatable. So again, it's kind of a cheating method of getting the inflatable to work, but it does work. So it isn't just the gas pressure that enters into that slide, it's actually ambient air that's used to help inflate it as well. You just happen to use the storage tank in order to supply the venturi action to make it work. But we can make these things also useful for us for sometimes for pop-out floats. I think I've got a video someplace that shows some pop-out floats being used. I can show you that maybe after break. But again, exclusively for emergency use only. The deployment of these things, again, the slide assembly is really in a pack, and then when you open the door to release the pack, it unfolds itself, and eventually a lanyard is pulled and it causes the gas to be released out of the storage cylinder. They've got a gauge on the circuit in order to monitor pressure, and as well, I think they also, for servicing, just like on the door assembly, the assist, they have a chart that indicates the recommended pressure for filling it up. And this just shows the deployment of it. Maybe just a little bit also, just before we take off for dinner, this shows you what might be used for emergency brakes in some aircraft. This is also really a normally powered system that would be hydraulic, and what ultimately controls the distribution of what makes the brakes work is a shuttle valve. So you can see the shuttle valve is at the brake actuator. If there's no hydraulics available, what we'll do is we'll release a gas charge. They show it as an air bottle, but in some cases it's a nitrogen charge, and we allow the gas to go to a brake control valve. The brake control valve is really a three-way valve. So it's like a hydraulic valve, except when the handle is released, the gas pressure that's used to make the brakes function is vented directly overboard. So the valve is kind of spring-loaded to the off position, and then you have to turn the handle in order to pour pressure into the brakes. Strangely, they don't directly use air or gas under pressure to the actuator for the brakes. They've got what they call a transfer tube. The transfer tube contains a quantity of hydraulic fluid. So what they're doing is they're using air under pressure to push a column of liquid to the shuttle valves in order to move them to the position for application, and then that actuates the brakes. And the handle in the cockpit is usually safety, or I should say shear wired, in order to kind of hold it in a closed position. What you do when you pull on the handle, you're actually breaking the shear wire. It's made out of brass, and then you can apply the brakes. Usually you've got enough gas under pressure in the cylinder for maybe 3, 4, or 5 applications of brakes, but that's about it. But this is how they do it in a lot of Boeing aircraft. Don't know what they do on Airbus, but this is kind of a common idea on a lot of Boeings anyway. Okay. They're showing you kind of the same thing in this illustration, but again, you're using hydraulics normally, and what isolates, or at least provides for normal function, would be hydraulics, but what they use is pneumatics for emergency application of brakes. Emergency application, again, if it's going to be a normally actuated system, separation is going to be by shuttle valves. And that's what I can give you. It's now close enough to 6 o'clock. Why don't you take a break until 6:45?